So last class we discussed about SN1 and SN2 reactions. So there are several factors affecting these reactions, and there are different types of mechanisms, stereochemistry in the reaction. So we discussed the stereochemistry and mechanism. So once again we are going to detail about this, okay? And what will be the factors affecting these reactions we are going to check. So mainly we know that in the SN2 reaction, it is the attack of the nucleophiles happening from the backside. Okay, so after that we know that here you can see some examples of the SN2 reaction. Here it is alcohol group, it is attacking here, and the chlorine is leaving. Here you can see some more examples of SN2 reactions. That is a thiol group is there. Either group is, if either nucleophile is attacking the halogen compound, that is haloalkanes, will get an ether, then iodine will leave. Like here you can see some more examples. Here you can see that. And what will be the stereo and the mechanism all we discussed. And we'll check with the stereochemistry. So we said the nucleophile is attacking from the back side. It cannot attack from the front side in the SN2 reaction because there is already a halogen group, isn't it? So halogen group is highly electronegative in the nature. They also having electrons, so they also are nucleophiles. So what will happen? A nucleophile already is in the compound. So another nucleophile is coming from the front side. The repulsion between the electrons occurs. So that's why it can only attack from the back side. Here it cannot attach from the front side. It can attach from only back side. So after the reaction, there is an inversion occurring. This inversion is occurring to reduce the steric hindrance or the charge, or to reduce that disorder. For that inversion occurs. This inversion is known as Walden inversion. You can see nucleophile is attacking here. Then what will happen? It is attached to the carbon. The transition state, the bromine also there. Here you can see the carbon is in sp3 state and it changed to sp2 here. It after the inversion it is again sp3. Here you can see that it is an umbrella like model. So after this leaving, what will happen? In order to reduce the steric hindrance in the compound, the inversion is occurring. You can see that. You can see in this step there is a partial bond between nucleophile and partial bond between that halogen group. It's an intermediate stage. So after that, in order to get the come back to the previous stage like this, it will inverted. And the factors affecting this SN2 reaction is, the first factor is the substrate structure. The substrate should be less bulky and should stabilize the transition state. For example, if we check the compound, here you can see a image of this. Here you can see the carbon attached to 3 hydrogen, so that is a methyl group, and it is ethyl, CH3 CH2 Br, so ethyl. Here CH3 CH3 CHBr, so it is propyl, and 2 branching is there, 2 methyl branching is there, so it is known as isopropyl. And 1 2 3 3 methyl groups attached to the carbon, so there are totally 4 carbons, so it is butyl. So 3 methyl group branching is there in the same carbon, so that is known as tertiary butyl. So there are different naming, so we studied the naming already. So if we check in this methyl, first one is methyl. If we check the here, this carbon is attached with hydrogen. We know that hydrogens are very small and they have less bulky, low molecular. If a molecule having less size, this is known as bulkiness or bulky. So the nucleophile can easily attach to the carbon. So because these are very small, so there is a space to attach. Here is, if we see CH3, one CH3 group is there, then two H groups are there. But it's okay, the nucleophile can attach with the carbon. But if you check here, two CH3 is there, but anyhow nucleophile can attack. It will get some space. But in the case of tertiary butyl, there is three bulky groups are attached the carbon. So already three bulky groups are there. So nucleophile cannot enter easily. So in SN2 reaction, the tertiary butyl is not favor in the SN2 reaction. So the SN2 reaction will occur most probably in the methyl group and tertiary methyl group and ethyl group, and tertiary butyl it will not favor the SN2 reaction. So the tertiary butyl will be less reactive. For example, if there is a door, if you want to move through the road, there should be some vacant space. But if two fat people are standing there, we cannot move through that door easily. So there is some hindrance. There is a hindrance, or there is some problems as to move easily. So there is no space. Similar case is occurring in the case of SN2 reaction. If there are bulky groups, it will hinder the the entrance of the nucleophile. So it cannot attack the carbon center. So in the SN2 reaction, reactivity will decrease if number of alkyl group increases. Then next factor is effect of nucleophile. The nucleophile having should contain more negative charge, then only it can easily attack. It should contain more electron pairs, then easily it can donate the electrons to the carbon, then only it can attach with the carbon. So it should contain more negative charge, that is more pair of electrons. So here you can see in the periodic table trends in nucleophile strength. We know that iodine, bromine, chlorine, fluorine all are nucleophiles. So increase down the periodic table, and the size and polarizability increases. If the size increases, the polarizability also increases. So in the periodic table, iodine can easily donate its electron pair towards the carbon, so it can attach with the carbon easily compared to fluorine. And similarly, if you can see OH minus having high stability because it having more negative charge. Here you can see an image. Iodine having high size, and it can easily donate its electron towards the chlorine, because if we compare fluorine is very small. It cannot easily donate its electron towards carbon because its nucleus having charge on the nucleus having the attraction on the valence electrons. So here the radius will be less, so it can easily donate its own electron towards the carbon. But in the case of iodine having high molecular mass, iodine have a high atomic size, atomic radius. So the nucleus of iodine having less attraction on the valence electron. So it can, in the case of iodine, it can easily donate its electron towards the carbon, and it can easily bond together with carbon. So the strength will be more. So if the size of the nucleophile increases and the negative charge on the nucleophile increases, the stable compound will form, the reaction rate will be increased. Here you can see the order. Then next one is the nature of leaving group. A similar case in the case of nucleophile, if the leaving group having high molecular mass and it is the ability to easily leave from the compound, for example, it can, the leaving group reactivity, here you can see leaving group reactivity increases. Fluorine is less reactive compared to iodine, because the same reason, because the iodine having high nuclear charge, less nuclear charge, iodine having high molecular mass. So what will happen, it can easily remove the carbon iodine bond will be can easily break. because it is a good leaving group, so it can easily remove. And next one is the solvent defect. The solvents are we are using solvents in the reaction. So there are two types of solvents: non-polar solvents and polar solvents. And the polar solvents again classified as polar protic solvent and polar aprotic solvent. Polar protic solvent which contain hydrogen, polar aprotic solvent which cannot contain, which do not having hydrogen with it. Here you can see in SN2 reaction we are usually using polar protic solvent because the first stage this for example OH, which contain OH or NH, because both having H. So what will happen here, first it will stabilize the nucleophile and it will slow down the reaction or slow down the speed of the nucleophile before the attachment of nucleophile here. It will stabilize that nucleophile. So we are using polar protic solvents here. We cannot use polar aprotic solvent in the SN2 reaction. So then let's check the stereochemistry of SN1 reaction. So in the case of SN2 reaction, we know that it is a biomolecular reaction. So what will occur? Because of that, we have to consider the character of or nature of nucleophile. Similarly, the nature of the substrate. But in the case of SN1 reaction, we know that it's a unimolecular reaction. So we need not to worry about the nucleophile, because it is only the rate of the reaction or the speed of the reaction only depending upon the substrate nature. And only three factors we have to consider. First one is the nature of substrate, and the second one is the nature of the leaving group, and the third one is the nature of the solvent. Here one example is given for the XN1 reaction. It is similar to SN2, no other difference, but there are mainly two difference. In the SN2 mechanism, nucleophile can attach only from the back side, but in the case of SN2 reaction, SN1 reaction, the nucleophile can attack from both front side and back side. Okay, here you can see it's an example. Here this first step, there are two steps. First step, the leaving group leaves, then carbocation forms. The carbon contain positive charge is known as carbocation. Then only our nucleophile attacks and we'll get the compound. And we know the kinetics and all, we already discussed this, because it depends only the substrate, not in the nucleophile. So here you can see that stereochemistry. It is our haloalkane. Here the first step is slow step. The chlorine will remove from here and carbocation forms. Then either it can attack from the front side, attack or back side. We'll get two types of compound. If it is attached from the front side, we'll get this one is back side. Attached from the back side, we'll get this compound. If it is attaching from the front side, we'll get this compound. And it is a chiral substrate. Chiral substrates means I hope all of you know what is that plane polarization and all. If the chiral substance, the carbon contain, if the carbon, this we know the valency of carbon is 4. So if it is attached with 4 different groups, then this carbon is known as chiral carbon. Here we can see 3 different groups attached with the carbon. So what will happen if the nucleophile attached from the back side, there is inversion of the configuration, and if it is one attached from here the retention, inversion and retention occurring in the SN1 reaction, but in the SN2 reaction only inversion is occurring. In order to this inversion and retention occurring, in order to delocalize the carbocation charge, in order the stability of the carbocation, we know that in this reaction carbocation is occurring. So in order to stabilize this carbocation, this